Good afternoon. Assalamualaikum and good afternoon everyone. Today we will continue with tutorial 3. The first question. What function is served by the GDTR? What is stored in GDT? What does it mean by GDTR? You can refer to the slides. About GDTR in slide number 4. GDTR means Global Descriptor Table Register. It holds the information that defines a table in a physical memory called the Global Descriptor Table, GDT. So, in summary, we can say that GDTR points to the Global Descriptor Table in physical memory address space. What it stores is the descriptors of the segment in the global memory, as mentioned in the slides. Number 2. Given the content of the GDTR is as the following: 0013000000FF, the descriptor for the LDT is loaded at starting address 00130040H. What should be the value loaded in the LDTR? So, from the questions, given the base of the GDT, you can find it from the given GDTR. So this is the GDTR given 00130000FFH. From here we can find the base of the GDTR, which is 0013 0 to 15 is this one, which is the limit. Okay, but the rest of it is the base of the GDT. In the question also given, the descriptor for the LDT is loaded at starting address 00130040H. Okay, so this one given, the descriptor for the LDT is loaded at 00130040H. So from this one, you can see what is the selector. Okay, from the descriptor for the LDT, the selector will be 0040H. So this is the value that should be loaded into the LDTR. Okay, we'll continue with question number 3. Which control register contains the MSW, most significant word? What must be done to turn on paging? So we can find actually the answer in this slide number 16. Again the question, which control register contains the MSW? The control register that contains the MSW is the CR0. It contains, not the most significant word, but it's the machine status word. It also contains the paging, that is the select bit. Okay. What must be done to turn on paging? Okay. So based on this control register, to turn on paging, we must set the PG and PE to 1. Okay, so this PE, protected mode enable, should be set to 1 to enable the protected mode, and then the PG bit, which is the paging bit, should be set to 1 as well. Okay. Okay, as mentioned in the slide, if we set PG to 0, memory paging is not selected. But if we set PG to 1, this will somehow enable the processor paging mechanism. Now, let's continue with question number 4. What are the names and sizes of the 3 fields in a selector? What does TI equal to 1 mean? So, you can refer to this slide number 18, registers with change functions. So this is the segment selector registers. It has the index, TI, RPL, and also RPL. Okay. So the question is, what are the name and size of 3 field in the selectors? So the 3 field in the selector, this is the selectors. So there are 3 field. First field is the index, this the RPL, requested privilege level, and then the TI, and then the index. Okay. So RPL, the size is 2 bits. Table indicator TI is 1 bit, and then the index is how many bits? The rest of it, okay, which is 13 bits. The index 13 bits. So index 13 bits, TI 1 bit, RPL 2 bits. So what does TI equal to 1 means? TI equal to 1 means use the local descriptor table. As mentioned here, TI, if it is 0, it is global descriptor table. If it is 1, it is local descriptor table. Okay, let us see question number 5. What happens when the following instruction sequence is executed in protected mode? Move AX 1007H, move into DS EX. So what happens is, when we move AX into 1007H, this will store the value 1007H to the register AX. Okay, the second one, move DS AX. The second instruction will load value 1007H from EX into the data segment selector register DS. Okay, so this is the data segment selector register. Okay, now the value that loaded into it is 1007H, which is equal in binary 0001 0000 0000 0111. Okay, so you map this binary to this segment data segment selector registers. Okay, and what happened is that you can see that RPL is 1, the next RPL is also 1, so you get RPL equal to 3, and then index is what? The 0, 1, 2. So start from here. From here to here is the index, right? So the index is how do we find the index? Okay, so from here the index is 0001 0000 0000. Okay, so if we count from the significant from the right here, okay, so this is 4 bit, this is another 4 bit, This is another 4-bit. Okay, so this equal to this is equal to 4-bit. This is 4-bit. This is 4-bit. So equal to 0 to 00 H. So this will be the index. Okay. So this causes the descriptor pointed to by the selector in the S to be loaded into the data segment descriptor cache. RPL equal to 3, because here RPL is 1, okay, index is 0 to 00H, and the selector descriptor is located in LDT. Because TI is equal to 1, so the selector descriptor is located in LDT, local descriptor table. Okay, let us continue with number 6. Assume that the above instructions select a descriptor that specifies the base as 0020000H and limit as FFFH if SI is equal to 0100H, what is the physical address of the data to be obtained from SI? So we want to find what's the physical address for the data to be obtained from SI. So given the base address as 002000H, and SI is given as 0100H, right? Physical address from SI will be just plus the base address with the SI value, and we get 00200100H. Okay. Number 7. Data segment selector registers select a descriptor at address 000100220H. The content of the descriptors are as follows. What are the limit and base of the data segment? So what's the limit and base? So, okay, for the answer we can refer to slide 42. This 42 describes the system segment descriptor. You can see we define the base and also the segment. Right? So and also the limit. Limit. So from the question we can see that what are the limit and base of the segment. So we refer to this slide. The base will be byte. This is byte 0, byte 1, byte 2, byte 3. So base is byte 2, byte 3, byte 4, and byte 7. Okay, as mentioned in the answer there. Base is byte 2, byte 3, byte 4, and byte 7. So if we map it to the answer, this is byte 0, byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, byte 7. Okay. So again, this is byte 0, this is 01, byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, and byte 7. And if we map, if we see what's the limit according to the slide is byte 0, byte 1, byte 6. Okay, this is byte 6. So the limit is byte 0, byte 1, byte 6. So this is byte 0 is 01, byte 1 01, okay, 0101, and byte 6, 0, 1, 2, 3, 4, 5, 6.